thank you, Kirill. So yes, as Kirill said, I'm sorry I can't be there in person, but my 3.5-week-year-old son is keeping me here in the UK. But I'm happy to talk to you on Zoom nevertheless. So actually, whom am I talking to? So I can see you, Kirill, and I see Stephen there. Hi, Stephen. So just give me some idea of who's in the room. Who am I talking to? Oh wow, okay, lots of people. Hi everyone.
So yeah, yeah, we have some more experienced and less experienced people, some students. So you may have to go into some basics a bit, but yeah, I suggested that if anything needs to be clarified at some point, we can discuss it in the coffee break, at lunch, and so on. So there will be people here who will be able to clarify some points about the talk.
Yeah, so I wanted to say up front that I'm conscious this set of lectures is slightly tangential from the themes of the other lectures, but I'm hoping nevertheless that in spirit it's at least similar, because so I've written here the goal of these lectures is to illustrate how relatively simple tools from analysis can be used to answer important questions in the numerical analysis of the Helmholtz equation. And of course, lots of the other courses that are going on as part of the summer school are about using tools from analysis in somehow applications. In particular, I guess we're just seeing Kirill talking about applications in material science. So I hope that thematically this fits.
Yeah, absolutely. So, in fact, I sort of introduced pretty much the Helmholtz equation. So
okay,
when you mention it again, it should be we should recognize it here from my.
Okay, great, great, and so I should say so that this series of these 3 lectures are based on an expository paper I wrote that's got this title and is available on the archive. And this paper in turn was based on part of a series of lectures I gave at ETH in Zurich last semester on this topic. So I mentioned this in particular because you can go in here and there are some proofs and things that I'll omit, but you can find the details in this article. Okay, so let's crack on. But if there are questions, Kirill, I'm relying on you to flag me down and get me to explain things as is necessary. So like I said, the stuff I'm going to talk about today is on a really simple today and the next few days is on the sort of simplest possible case based in this paper, but the ideas that I'm going to talk about are applicable much more generally, and somehow there's now a sort of growing body of work done by myself and others on this. So these are the sort of my three collaborators on this. This is Jeff Gałkowski. I should say this is Jeff Gałkowski. This is David Lafontaine, and this is Jared Wunsch. And we started off with David, Jared, and I having a paper. Then the 4 of us had a second paper we just revised recently. And then actually yesterday I had time, despite my 3-week-old son, we had time to write a third paper, which we put on the archive yesterday. Which again uses the ideas I'm going to talk about in this course. And actually, in some sense, I would argue this third paper somehow sort of settles this question, or this question I'm going to pose today in sort of almost all practical cases for the Helmholtz equation, or at least settles it to the extent that is conceivably possible right now. Right. So what's in this talk? So today I'm going to talk about this model Helmholtz problem. I'm going to talk about this numerical analysis question. So it's interesting because I'm conscious this audience is a bit more, is more an analysis audience. And so I thought, well, perhaps I should start off talking about these analysis tools and the analysis result about the Helmholtz equation that we're going to use to answer this question. But I thought, well, actually, no, I want to introduce the numerical analysis question first to kind of give the motivation. And then towards the end of these 3 lectures, I'm going to give you the analysis results. So what that's going to mean is today's lecture and the first half of tomorrow's lecture are going to be unfamiliar things, I think, to many people. But then the second half of this course is going to be much more familiar. Okay, so that's just saying, if you, yeah, the more familiar things are coming down the line, I expect, for most of you. Okay, so that's the numerical analysis question. And then today we're going to assemble these background results to tackle that. And I should say, just, you know, I'm sitting in the dark here in this room, and it's because it's a bit hot here. It's 27 degrees here in this room, so I'm keeping everything kind of dark and away from the sun as much as possible. So, but you'll be pleased to know that 2 minutes before giving this talk, I put a shirt on. So, but you know, if it gets much hotter, I might have to lose the shirt, just to warn you. Okay, so Kirill said you said that you met the Helmholtz equation. So let me immediately tell you then this model Helmholtz problem that we're going to consider. So it's really the simplest possible Helmholtz problem. So we're going to say, given some function f in L2 with compact support Rd, find a function u in H1 log of Rd such that Laplacian of u plus k squared u is minus f, and so that's the PDE in the whole, satisfied in the whole of Rd, and then we're going to have a condition at infinity, what's called the Sommerfeld radiation condition. So that's that k inverse du by dr minus IU is little o of 1 over r to the d minus 1 over 2, as r, which is the modulus of x, my position vector, tends to infinity. Okay, and this condition's got to hold uniformly in x over r. Okay, so that's this model Helmholtz problem, and in fact, I'm actually going to divide my Helmholtz equation through by k squared. So I'm going to write it as k inverse Laplacian of u plus u. Okay, and then I change my f appropriately. So divide the original f by k squared to get the Helmholtz equation in this form. Okay, and so what I'm doing that is I want to weight each derivative with an inverse power of k. Okay, so you see, I did that already in this radiation condition here, but I'm going to do it in the PDE. Okay, but but this is none other than the standard Helmholtz equation, and so it's a well-known result due to Relic that the solution of this problem here exists and is unique. And so of course I want to say that this problem is so simple that you can just write down the solution of it explicitly, right? So when d is 3, u is just the integral. So k to the minus 2 is just the convolution with the fundamental solution. So e to the ik mod x minus y over 4 pi x minus y f of y dy. Okay, so later I'm going to talk about solving this model problem numerically using the finite element method. I'm going to tell you what that is. But of course, in practice, you would just actually take this explicit, if you wanted to know what it is, what the solution is, you've got this explicit expression for the solution. The whole point is the ideas and techniques I'm going to tell you about generalize to situations where I can't just write down the solution explicitly. Okay, so just for simplicity of exposition, I'm considering this, as I said, simplest Helmholtz model problem. Okay, and so this condition infinity, this radiation condition, so mathematically you can think of it as a condition that ensures well-posedness of your solution, but then physically you can think of it as the condition that waves move outwards from the source, which in this case is f, out to infinity. And so Kirill, did you explain this, or do you think people are comfortable with this, or should I explain where this radiation?
I only mentioned that the equation that you have just introduced as the Helmholtz equation.
Yes.
in the whole space would require some additional conditions.
Okay.
I didn't say what those conditions are. I was looking at arbitrary solutions.
Okay. So let me. I'm just going to take in 2 minutes to explain the meaning of this radiation condition. I'm sure there are people in the audience who know what it is. In that case, I apologize, but just to make sure we're all on the same page. So here, if I start off with the wave equation, so I'm writing this as this sort of capital U as a function of space and time. If I look for solutions of the wave equation, capital U of x to t, in the form little u of x e to the minus I omega t, then little u satisfies this Helmholtz equation with k, this wave number, as omega over c, and okay, with this little f, okay, as so with k, and I have to assume a similar, because I'm not going to write it, I have to assume a similar time harmonic dependence of my source, capital F. So actually, let me rewrite it. I should write it. The f of xt is, let's say it's going to be k squared f of x e to the minus I omega t. Okay, so that then I get my Helmholtz equation from the wave equation, and one can show that this radiation condition implies that U has the following asymptotic expansion for large R. So U of x is e to the I k r over r to the d minus 1 over 2, then some function, okay, I put capital F naught x over r. So if some function of the non-radial variables, then order 1 over r, this is as r tends to infinity. And so now we see if we go back, so if we've got our solution of the Helmholtz equation, it satisfies this radiation condition. We go and look at what that implies for the corresponding solution of the wave equation. We see then that capital U of xt, so I've got to put in this e to the minus I omega t dependence, and I see that it's e to the I k r minus ct, okay, r over d minus, sorry, 1 over r to the d minus 1 over 2, blah, 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 blah. And so you see then this is now a function here of r minus ct. That's a wave moving in the positive r direction as time increases. Okay, so i.e. positive r direction means away from the origin, away from the source f. Okay, so we see then that this condition is then sort of, the physical interpretation is that waves are moving away from the source towards infinity. Right, so that's our model Helmholtz problem. Now we're going to find the variational formulation of this model Helmholtz problem. So I'm sure that all of you have met these second order linear elliptic PDEs before, like Laplace's equation or Poisson's equation, and how you found the variational formulations was you multiply the PDE by a test function and integrate by parts. And the natural space then was this H1, right? H1, where both the function and its weak derivative are in L2. And we're going to do the same thing here. The only sort of subtlety is that the Helmholtz equation is posed in this unbounded domain. It's posed in RD, and actually U is not in H1 of RD. It doesn't decay quick enough for that. So instead, what we're going to do is we're going to fix some large R such that the support of the data F is contained in the ball of radius R. And if I were doing a Helmholtz problem with like obstacles or variation of variable coefficients, I would make sure that all the obstacles and all the variation of coefficients were also in this large ball. And then now on this large ball, I take the Helmholtz equation, I multiply it by a test function, and I integrate the parts, and I get the following variational formulation. So the task is to find, I'm going to say U tilde in H1 of the large ball, B sub R, such that A of U tilde V is f of v for all v in H1 of the large ball, where, so what's this sesquilinear form, A u tilde v, so it's the integral of the ball of radius r, so k to the minus 2, grad u tilde, that's a bit of a crap tilde, dot grad v bar minus u tilde v bar. Now I've got some term on the boundary, on this outer boundary of this ball, and it involves, so okay, what is it? It's that it involves this map I'm going to call DTN. Okay. So here, these angle brackets mean the duality pairing, but if you don't know what this means, just think L2 in a product on the boundary of this ball, and this map DTN. So this is the exact Dirichlet-Neumann map for the Helmholtz equation in the exterior of a ball. Okay. So let me write down that. So the definition of this map DTN is, okay, given some function g in h1/2 of the boundary of the ball, let w, okay, and again in h1 log of the exterior of the ball, be the solution of this homogeneous Helmholtz equation in the exterior of the ball, with w satisfying, so w, the trace of w being equal to g on the boundary of the ball, and then the map DTN of g is defined then as k inverse. I'm going to weight my derivatives with k, then the normal derivative, which is the radial derivative of w on the boundary of the ball. Okay, so DTN maps h1/2 of the boundary of the ball to h minus 1/2 of the boundary of the ball. And so if you don't know what these fractional Sobolev spaces are, then don't worry about it. Okay, and so what the point is that by separation of variables, I know what this solution of this Helmholtz problem is. I can write it as a Fourier series. And so I can have an explicit expression for this map DTN in terms of Fourier series, Hankel, Bessel functions. Now, of course, for this very simple model problem, we've got an explicit expression for our solution anyway. But when you have these more complicated Helmholtz problems involving obstacle scattering or coefficients of scattering by variable coefficients, you can still do this trick, namely formulate the variational formulation on some finite ball using just the Dirichlet-Neumann map for the exterior of this kind of constant coefficient Helmholtz equation problem. Okay, so I'm saying this variational formulation works for much more general Helmholtz problems too, or this idea of formulating it on this large ball. Okay, and so that was my sesquilinear form, and then my anti-linear functional on the right-hand side of my variational problem is just the integral of f against v bar on the over the ball. Okay, so I'm hoping that people who have seen variational formulation of like second order linear elliptic PDEs before will be somehow happy with this. The only kind of the non-standard thing is this using this Dirichlet-Neumann map on this outer boundary. And here I was careful. I wrote find this u tilde because okay, we need to show then that u tilde is the restriction to the ball of this Helmholtz solution u defined as the solution of the full space problem. Okay, but this is straightforward to check. You can see the details in this article. Okay, Kirill, are you with me?
Yes.
Good.
Yes. So I mean, it's getting a bit technical, but in principle, some of these objects are recognizable from my first lecture. So.
Okay, good. So yes, so yes.
K, the number K, the wave number.
Yes.
It came up. It was just in my case, it was the modulus of K because K was a wave vector.
Okay. Okay. Yes. Yeah. So here we got this wave number K, and I should have said that I'm interested in studying this problem, this model Helmholtz problem, and more complicated Helmholtz problems. In the case when K is large, I'm going to think about these. The case when when the wave number is large, what we saw here that the wave number is related to the frequency of the waves in the time domain, and so we often call this the high frequency limit as K gets large.
Yeah,
okay?
So I referred to this at the very end of my lecture as the short wave limit. So because K is the 2 pi over the wavelength.
Yeah, exactly. This is short wavelength, high frequency.
Yes.
Yeah. Yeah, and so I'm just going to repeat, because this variational formulation really is somehow we're going to use it all the time. So I'm just following to formulate this variational formulation. I'm just following this standard idea of multiplying with the PDE by a test function, integrating by parts. But the subtlety is that I can't do this over the whole domain where the PDE is posed, which is RD, because the solution is not in H1 of RD. So I have to introduce this artificial boundary, the boundary of this ball of radius R, and then on that outer boundary, I'm okay, or I can formulate a variational formulation as long as I involve this exact Dirichlet normal map for the Helmholtz equation in the exterior of the ball that we will treat. I mean, in fact, it is, you can write it down explicitly. We're just going to treat this as some known operator. Okay. So that's the variational formulation. That, of course, analysts use the variational formulation, but also why I'm talking about it now is because the variational formulation is the basis of this very popular method for solving PDEs numerically, which is called the finite element method. And so the finite element method is actually a special case of this, the Galerkin method. Okay, so what we're going to do to now compute approximations of our Helmholtz problem is we're going to choose. So if we choose Hn, let's say n is 0 to infinity, it's going to be a sequence of finite dimensional subspaces of our Hilbert space we're working in, H1 BR. Okay, and these are going to be chosen such that informally, as n gets larger, these spaces fill up the space H1 BR. Okay, so let's write that down more precisely, such that for all v in H1 BR, the limit as n tends to infinity of then the smallest error one can hope to incur in approximating v by an element of the subspace Hn is 0. So like I said, this is just the idea that these finite dimensional subspaces fill up the space H1 BR. Okay, so the fancy terminology for this is that the subspaces are asymptotically dense in the original Hilbert space. Okay, and then the Galerkin method is so I go back to this instruction in this yellow box here. Okay, find a u tilde in H1 BR such that a u tilde v is f of v for all v in H1 BR, and I just replace the Hilbert space by the finite dimensional subspace. Okay, so I say find un in Hn such that a un Vn is f of Vn for all Vn in Hn. Okay, so as you might get the impression, my research is at this interface between analysis and numerical analysis of the Helmholtz equation mostly, and I give talks both numerical analysts and analysts, and whenever I talk to analysts, I say to them, okay, now I'm going to tell you about this numerical method, the finite element method, and I can see the sort of looks of fear in their eyes. But then, you know, I say, well, it's just the same thing as this. I just take my yellow box instruction for my variational formulation and I replace my Hilbert space with this finite dimensional subspace, capital Hn, and then I see them all relax. You see, so that's why, unfortunately, I can't be in the room with you now. But I'm hoping you're all. Maybe some of you were scared when I started talking about finite element method, but now you see it's just this yellow box bait that was the instruction for the variational formulation, but instead now working in this finite dimensional subspace. Okay, good. So that's this method. That's the Galerkin method in general for then getting a sequence of approximations un to my solution u. But I still need to specify what finite dimensional subspaces we're going to use. Okay, and so we're going to consider. So I can even change color here. So we'll consider Hn consisting of piecewise polynomials. Piecewise polynomials. Okay, so I take my domain, which is, okay, in this case, this ball of radius r, and I chop it into lots of little pieces. Okay, so I'm going to draw some. In fact, people use triangles, so I'm going to chop it into lots of little triangles. Okay, you get the picture. And the sort of so this is then a mesh, and the diameters of the little pieces I'm going to call h. This is going to be called the mesh width, and I'm going to assume that somehow all the pieces are roughly the same size. So this notion of a mesh width makes sense. And on each little piece, my subspace is going to consist of piecewise. So on each little piece, the subspace is going to consist of polynomial. So my subspace Hn consists of functions then that are globally in H1, so they're going to be continuous, but on each little piece are a polynomial. And I'm going to talk about this, the degree of the polynomials be p. Okay, so I've got the mesh width h and the degree of the polynomial p. So now I have three choices to increase accuracy. So, and these are going to correspond to the h fem, the p fem, and the HP fem. So in the h fem, I increase accuracy by decreasing h. Okay, so I make so my sequence of subspaces, as n tends to infinity, h, this mesh width, is going to get smaller, and the polynomial degree p is going to be fixed. Okay, and then the p fem, p is going to go to infinity. I'm going to increase p as n tends to infinity, and I'm going to fix h. And the HP fem, I'm going to let h go to 0 and p go to infinity as n tends to infinity. Okay, so these three different kind of choices of things you can do, and I want to note for later that the total number of degrees of freedom is proportional to P over H to the D of my subspace. Okay, again, I'm assuming that all the little the meshes, the elements of the meshes are all roughly the same size. Then the total number of degrees of freedom is like P over H to the D. Right. So here's the Galerkin method. It's this yellow instructional box here. I'm talking about these piecewise polynomial subspaces. So that's then the definition of my, that's the definition of the finite element method. And what's the goal? Okay. What's the goal? Well, the goal is for the sequence of solutions that you compute. So you're given your sequence of subspaces, you got a sequence of solutions, and you want these solutions to be quasi-optimal. Okay, so I'm saying the goal is quasi-optimality, and that is that there exists some constant, I'm going to say C Q subscript QO for quasi-optimality, and some n naught natural number, such that once my subspace dimension is greater than or equal to n naught, I have that the error I commit in approximating U by the Galerkin solution UN is bounded by some constant, sorry, by the constant CQO, times then this smallest possible error I can incur in approximating U by an element of the subspace. Okay, so if the method, if the method were optimal, then UN will be such that this error really was equal to the best approximation error, but we sort of settle for being optimal up to this constant CQO. Okay, so that's quasi-optimality. So now, having picked on Kirill, I'm going to pick on the only other person in the audience I know, I think, which is Stephen. Stephen, are you with me?
I am with you.
You're with you. Good, good. Okay. And so here I actually haven't specified what norm I'm using on H1. And actually, I want to define more generally, I want to define norms weighted with K. Okay, because so let me write down the definition. So I'm going to write the HM norm on BR, okay, weighted by K. So this is an R. It's a K. Is going to be defined by, so it's just the standard. I'm running out of space here. But it's the standard HM norm, but now I weight all derivatives by K. Okay, so it's this, look at it, I'm right, just out of space. Disaster, foiled. Okay, this is the substance with 0 mod alpha less than we got to M. Okay, so you just take the standard definition of the HM, and then you shove in a K inverse every time you take a derivative. Okay, and this is because, so I'm expecting my solution of my Helmholtz equation to oscillate with frequency K. And so somehow every time I take taking a derivative of a function oscillating at frequency K is going to incur a power of K. So weighting derivatives by K mean that all the derivatives somehow should then be comparable. Right. So this is the definition of the finite element method. It's the Galerkin method, this yellow instructional box here, with piecewise polynomial subspaces. And now the question, right? I said in this plan, right? Where's the plan? Here's the plan. I said there's going to be a question somewhere. It's like in the courtroom dramas, right? When they say, you know, Your Honor, is there going to be a question anytime in our future? And so, yes, here is the question. Okay, the question we're going to consider and answer in these lectures today, tomorrow, and Friday is, for what H and P, okay, let's start again. So I'm going to consider solving a sequence of Helmholtz problems as K increases. And then the question is, how should I decrease H as a function of k and or increase p as a function of k, how do I need to do that so that I have quasi-optimality with this quasi-optimality constant independent of 1 as k tends to infinity? Okay, so I want to sort of solve this sequence of Helmholtz problems with uniform accuracy in this high frequency limit, but what do I need to impose on this mesh width h and this polynomial degree p as k tends to infinity for that to attain that uniform accuracy? Okay. See, I'm pausing now. I'm pausing whether to get audience participation. I'm going to ask people what they think. This is always dangerous, but I'm going to go for it. Okay, let's consider the case when the polynomial degree p is fixed. Okay, so I just like take piecewise linear, let's say polynomials, and now I'm going to be decreasing h. I'm going to increase accuracy by decreasing h. Okay, so this is it. And again, I hesitate. I'm going to pick on Kirill again. I'm sorry, Kirill. It's either you or Stephen. So Kirill, when p is fixed and I decrease h, how do you think? How should I tie h to k as k increases to maintain accuracy?
1 over k.
1 over k. So that's exactly the answer I wanted you to say, Kirill. I'll pay you the money we arranged when you're back in Bath. So yes, so Kirill has said 1 over k because given a function oscillating with frequency k, we expect that it needs k to the d degrees of freedom for kind of uniformly accurate approximation as k tends to infinity. Okay, so for example, h going like 1 over k and p fixed, p constant, right? Because remember, I told you that the total number of degrees of freedom were p over h to the d, right? This is the total number, the number of degrees of freedom of my piecewise polynomial space. Okay, so if p is constant, h is 1 over k, then this is k to the d. Okay, and so let's just draw. Look at it. You came in expecting a talk on numerical analysis. There'll be like computer drawn pictures, but no, I'm going to subvert expectations here and draw some hand drawn pictures. So here's my 1D oscillatory function with frequency k, and then so my son, he's only 3 weeks old, so we've got to wait a few more years before he can do some sort of join the dots exercise. But then we can ask him to do some join the dots exercise to then sort of approximate this by piecewise linear, continuous piecewise linear polynomials. But now, if I increase k, look at that, almost. Okay, well, let's go with it. Then if I don't decrease h, I'm just going to get garbage here, right? So I need to decrease h, and in fact, I need to decrease h proportional to 1 over k. Okay, and so this is sort of, I'm going to write CF, the Nyquist-Shannon. In fact, Nyquist-Shannon Nyquist-Shannon-Whittaker, because apparently this sampling theorem was sort of discovered and rediscovered by various people. Okay, so exactly as Kirill said, we expect, when p is constant, you need h going like 1 over k, and it's because given an oscillatory function, I do indeed need k to the d degrees of freedom to approximate it well. But my numerical method, it has to find this function. So you're not just given it, you have to find the function or find an approximation to the function. And actually, for this H version of the finite element method, having H go like 1 over K is not enough for this goal of K independent quasi-optimality. Okay, so there should be, let's put a big here, a big red but here. But for this H fem with, let's say, P is 1, piecewise linear, continuous piecewise linear polynomials, you actually need H to go like 1 over K squared for this for this goal, right? For CQO to be independent of 1. And when P is greater than 1, I need H to go like, so it's K to the minus P plus 1 over P. Okay, so you see that as P gets large, this becomes close to 1, so you get close to this 1 over K threshold, but you don't get there. Okay, so here, so let's go here. So this implies that the number of degrees of freedom is proportional to K to the P plus 1 over P to the D that is much greater than K to the D. Okay, and this is what's called the pollution effect. Okay, so I'm hoping, let's see. Yes, I've got a concrete example here. Okay, so here, let's look at the left-hand plot. Okay, so the left-hand plot is then, so it's actually a more complicated model problem than our, so these numerics are done actually for scattering by a ball, actually. So by a ball, but we'd have same results for our model problem. And so we're solving it exactly as I said with these piecewise polynomials. It's the H version. So I've got P. So here's the results for degree 1 polynomials, and you see, and this left hand, so this left axis is exactly this quasi-optimality constant QO. So it's the ratio of the lurking error and this best approximation error. And you see when HK is constant, as Kirill suggests, and as you sort of expect, this error, this CQO grows with K. Okay, and then it's only constant here when you have HK squared is some constant. Okay, and in fact you see that this yellow line HK squared is constant. We're not going to large enough to as large values of K as we go with this. Okay, HK is constant here, and this other threshold, this H going like K to the 3 upon 2, because because the computer on which these computations did kind of ran out of steam, because this computation here is requiring more degrees of freedom, right? It's, given K, the degrees of freedom are more.
So my answer was ultimately incorrect.
Yes, yeah. Yes.
The correct answer is 1 over K squared.
Yeah. So when P is 1, yeah, when the polynomial degree is yeah. So it gets closer. Yeah. So it gets closer to 1 over K as P increases, for following this rule here.
Wait, you want? Can I ask about this?
Hi. Yeah.
So basically, would have been right to take a smaller and smaller problem. So you kind of rescale the whole problem to a smaller domain. Then you would be right, because it's pollution global. It's not a local effect, right?
So sorry, I can't quite hear you. You say about rescaling the problem.
Can you hear me now?
Mm-hmm.
The fact that, so basically what I'm asking is, would Kilo be right if you were to take a smaller domain as you take the H smaller, it actually change the problem? In other words, is the fact that you need to take K squared, is it actually due to a global effect rather than a local effect? That's the right way to think about it. Why?
So certainly we should be thinking of keeping so that the same domain or the same as a function right hand side with the same support, and then increasing k, because of course we could be sort of, if we sort of rescaled if we increase k but rescaled our obstacle, then somehow you're not actually getting a high frequency effect.
Right, I agree.
Is that maybe a?
I guess.
Yeah, and
I guess my question is, I guess maybe I should take too much time, but the fact that it's space squared instead of k is a global effect of how the pollution thing in the problem, right?
So you can indeed think of it as this sort of build up of this dispersion error, right? So you have your frequency or your wave number k, and your numerical method is essentially computing some approximate wave number, and it's the sort of the difference between these two things is then building up over space to then cause the solution and the numerical solution to kind of get out of phase. That's one way of thinking about it.
The intuition was coming from the idea of approximating functions only, rather than actually finding the solution and seeing. Yes.
Good. Yeah. So for sure. Yeah. So here, another way to think about it is, this best approximation error, right? This smallest possible error you could hope for in approximating your solution U in the space. This is controlled when h is 1 over k. For p fixed, this is controlled, h is 1 over k. U is given. Then that's an approximation issue, as you say, h 1 over k when p is fixed, great. But so what this is illustrating is that it's not just this approximation issue, it's, as you say, it's a more sort of global effect. Okay, I think I'm gonna move on in the interest of time, but if I didn't answer your question properly, then tell me by some means. Okay, so this is the numerical results with the quasi-optimality. Here, we're actually looking at the relative error. So this is the relative error for some sort of physical class of data, and it's just very quickly to say again, HK is constant. This relative error grows, right? So it's not that we're using some sort of crazy measure of the error. Engineers will sort of use relative error, and again, this pollution effect exists because this line is increasing with k. And I want to highlight immediately that this topic, this question, how should I be decreasing h or increasing p with k as k tends to infinity to maintain accuracy, has been studied for a long time. So there's these papers by Eilenberg and Babushka in the 1995, 1997 in 1D. So using explicit calculations on 1D, one-dimensional Helmholtz model problems, where they sort of then found the answers to these thresholds that I told you about. This threshold here, and 1 over k squared for p is 1. They found these in 1D, and just again, well, to illustrate, that these papers got lots of citations. This is a real kind of fundamental issue. And then in 2010, 2011, Markus Malik and Stefan Sauter, and again in these papers with lots of citations, what they showed is actually that the HP FEM, let me write it down because it's important, the HP FEM does not suffer from the pollution effect. Does not suffer from the pollution effect. And this was a really big result. So what they showed is that if HK over P is sufficiently small and P grows logarithmically with K, then I get CQ0 greater than CQ0 independent of K. Okay, so let's just before I'm going to write it up here. We had that for fixed P to get this quasi-optimality independent of k, I needed h to go like k to the minus p plus 1 over p. Okay, so what that showed you is that large fixed p is helpful, and here they show that actually that if you're increasing p logarithmically with k, then you really get rid of the pollution effect. Why is that? Because remember, the total number of degrees of freedom is like p over h to the d, and then somehow that is by this, it means I can make a choice. I can make hk over p equal to this constant, and this can then just be proportional to k to the d. Right. So that's the question, this numerical analysis question, and we've sort of got our answers, right? That the H version of the finite element method suffers from the pollution effect to an extent that we understand, but the HP method FM does not suffer from the pollution effect. And so these Mellin-Gonzalez papers were to do with this constant coefficient Helmholtz equation. So that I wrote down before. In fact, this first paper was exactly on our model problem that we're studying. So just in full space, no obstacle, no coefficients. And then this second paper was included the case of an exterior of a Dirichlet obstacle. And I first got into working on these questions to try and extend these results that were for this constant coefficient Helmholtz equation to the case of a variable coefficient Helmholtz equation. So problems with a variable wave speed. And so that's what these papers with David, Jeff, and Jared were about. But then in the course of teaching this lecture course at ETH in the second semester, autumn semester in 2021, I discovered how actually that this first Mellin-Gonzalez result, just for this model problem we had earlier, how you could do a really simple proof for that result, just using sort of elementary properties of the Fourier transform. And so then I wrote that article, that expository article, and then that's the material that I'm delivering to you in this course. Okay, so that's what we're going to cover in the next 2 lectures. We're going to prove this result, that HPFM does not suffer from the pollution effect for our model problem, but in a simpler way than Mellin-Gonzalez did, or using simpler tools. Right. So I think I started about 1:45. So if it's so I'm conscious of the time. If it's okay, I'm going to write down just two more slides or boards, which will take about 5 minutes, and then I'll stop there for today. Is that okay, Kirill?
Yeah, go for it. Thank you.
The master of ceremonies, Kirill. Right. So the first of these 2 slides is now, what information do we need going forward about this Helmholtz variational formulation? Okay. So remember that this was so we wrote our Helmholtz, we reformulated our model Helmholtz problem as finding, okay, so before we had finding U tilde in H1 of BR such that A U tilde V is F of V for all V in H1 of BR, but somehow since the solution U tilde is just the solution of the full space problem restricted to BR, I'm going to get rid of the tilde. I'm now just going to have call the solution U, whether it's on the ball of radius R or the whole space. Okay, so we need this fact, okay, that we have from Relic via the full space problem, that the solution exists and is unique. We're going to need that this sesquilinear form A, this creature here, is continuous. So continuity of A. So okay, so let's write it out properly or rigorously. So it's going to be given K naught and R naught, there's some constant C cont greater than 0, such that for all K larger than K naught and for all R larger than R naught, the modulus of AUV is bounded by this C cont times then the H1 norm of U, okay, the H1 weighted with K norm times then the H1 norm of V. Okay, this is for all UV in H1 BR. Okay, so remember that this sesquilinear form had the bit involving the gradient of U and just U, and so here these parts you just deal with using the Cauchy-Schwarz inequality. Now there was this part involving the Dirichlet-Neumann map, and so you do need some inequality to do with the Dirichlet to Neumann map to prove this, but this is not so difficult, and we're just going to take it on trust. And yes, and of course just noting that before, again, when you study these second order linear elliptic PDEs like Laplace's equation, Poisson's equation, you will have shown that the sesquilinear form was continuous in H1. And then the third thing we need that the sesquilinear form satisfies a Gaudian inequality or Guardian inequality. What's the pronunciation? Guardian inequality, I think.
Gordon.
Okay.
Yeah, it's because it's an A with an
Say again.
Yeah, it's Gordon. Gordon is Norwegian.
Gordon. Okay. Good. Look at that. I should be, expelled from the mathematical society or whatever that I'm involved in because I can't pronounce the Gordon, or at least kicked out of the analysts. The analysts will now reject me, right? Because I can't pronounce it. Okay. So here, this is that. Okay. So I just said, when you study a Laplace equation or Poisson's equation, you stick it in variational formulation. You prove the sesquilinear form is continuous. You also then prove it's coercive. But here, this Helmholtz sesquilinear form is not coercive. I cannot bound the real part of AVV below just by the H1 K norm squared. I need to have a multiple of the L2 norm as well. Okay. So that's then this Gaudian inequality. Right, final slide here. What information do we need about the Helmholtz solution operator? Okay, so we know, I've told you that the solution of this model Helmholtz problem exists and is unique, and actually the problem is well posed, so the solution depends continuously on the data. So U in my H1 K norm is bounded by, there's some constant C sol such that U in H1 is bounded by F in L2. But now I want to know what C sol is, and importantly, how it depends on K. Okay, because like I said, I'm interested in these problems when K is increasing. So now there's a theorem. So this question of how does the solution operator of the Helmholtz equation depend on K? This is a classic question in applied maths. I mean, still, people. I mean, I've written papers write papers on this regularly. In different circumstances. This is still a subject of kind of active investigation. Has been for and people have been thinking about it for many years. So in this setting of just no obstacle or coefficients, just the Helmholtz equation in full space, there's a nice bound on C sol that was proved by Kathleen Morovitz of the Courant Institute So there's a paper in 1968, which is joint with Donald Ludwig, and then Moravitz in 1975 proved more bounds on the Helmholtz equation in a solo author paper. And in this setting, her argument shows there's a nice explicit bound. So C sol is bounded above by 2 Kr, and then this factor, so 1 plus d minus 1 over 2 Kr, all squared, and then square root of this whole thing. And so it's in particular, when Kr is large, this C sol is basically Kr, bounded by a constant times Kr, and you can show, just using a simple kind of simple construction, that C sol must grow like Kr as this quantity Kr increases. Okay, so basically this K dependence or the Kr dependence is sharp here. Okay, and so how you prove this is, it's a very nice argument. You just multiply this Helmholtz operator, so the Helmholtz equation, by a carefully chosen test function. So multiply it by x dot grad u minus ik, okay, beta u plus alpha u. For some alpha and beta you then got to choose, and you integrate by parts. Okay, and so in the appendix of this paper, so I said I was basing this talk on this expository paper. In the appendix to that paper, I then write out this argument very explicitly. So again, it's just using integration by parts is a bit fiddly, but I think it's nice to get then this very explicit bound here. And then just finally, so the final result of today, I want to note that this was a bound on the H1 norm of solution U. I want to note that we can then get a bound on the H2 norm of the solution. Just so in full space, you can just use the Fourier transform. Again, the details are in the paper to show that, well, the details, but this is the standard result in the paper to show that then the H2 norm of the solution U is also bounded by some constant times Kr. So again, strictly it's given K naught, R naught greater than 0, there's a C greater than 0 such that this is for all K greater than or equal to K naught, for all R greater than or equal to R naught. Okay, and I just want to note that we're seeing the benefits of weighting our norms with K, right? We're using this weighted norm here, H1K, we're using the weighted H2K norm, and the consequence of using these weighted norms is that, that the solution operator measuring the H1 norm, this constant is like Kr, the constant in terms of in front of the data. Here I'm measuring the H2 norm, the constant is still in Kr because this oscillation in K, this fact that taking derivatives of U respect to K would normally incur powers of K, that's taken care of by the weight in the norm. Right, so that's all. That's actually all I wanted to say today. So it's got a good timing, because I think I've spoken just for about an hour. So just to recap, our sort of goal of what we're heading for in these lectures is to show that this HP FEM does not suffer from the pollution effect, right? That you can actually solve this Helmholtz model problem with number of degrees of freedom going like K to the D. And this is the result that Marcus Melling and Stefan Zauter proved in 2010, and we're going to sort of present a proof of it, which is somewhat simpler than their proof. And I'll talk then in this final lecture about how the ideas then of the simple proof generalize to these more complicated setups that we've been able to study recently. Okay, that's it from me today, but here, of course, there's an opportunity for some questions, short questions, but I'm conscious you've got coffee. But
yes, any quick questions?